Hello and a warm welcome back to my YouTube channel. Trust you're all well and in good spirits. Don't forget, make yourself happy and press like, everything's good. So this is my first videos on GCSE physics. Hope you found it useful, and this is just to support the teaching currently on the IGCSE 0654 syllabus for physics coordinated science. So first question is, which of the following is not an electromagnetic wave? So we've got gamma, sound, ultraviolet or X-rays. So gamma rays, looking pretty good. Sound waves are longitudinal. Ultraviolet is clearly on the electromagnetic spectrum, as are X-rays. So clearly the correct answer is going to be sound waves, because they are longitudinal. Okay, nice and easy to begin with. What type of electromagnetic waves do our eyes detect? And this is often forgotten, that we are actually viewing on the electromagnetic spectrum, and clearly this is visible light that we sense with our eyes, that we have evolved to use. What is a practical use for infrared waves? One that is not there is for use by the military for nighttime operations, but that one's not there. So what do we have instead? Start at the bottom. Is it used in satellites? No, that's microwaves. Medical imaging? No, that can be X-rays. Energy efficient lamps is visible, so I'm hoping the last one is for infrared waves, and indeed it is. It is for cooking food. You may have seen this from warming plates, etc. They often have red lights above the food to keep it warm, particularly in hotels where they've got lots and lots of food to get through. Okay. Scientists have detected radio waves emitted from a distant galaxy. How exciting. Some of the radio waves from the distant galaxy have a frequency of 1,200,000,000 hertz. That's a huge number. Why have they given me such a huge number? It's not very helpful. Well, the question's quite simple. Okay. So, which is the same as 1,200,000,000 hertz? Which is the same? So count the decimal places. I can count 3, 6, 9, 10. So it's 1.2 by 10 to the 9, isn't it? And we've got giga. Do you know what giga means? Yes, correct. Hopefully you're correct. Giga is 10 to the 9, so that's promising. Because kilo is 10 to the 3. Mega is a wonderful word and is 10 to the 6. And milli is a small 10 to the minus 3. So clearly 1.2 by 10 to the 9 decimal places. We can see that at the top. Easy peasy. The answer is 1.2 gigahertz. Happy days. Right then. Radio waves travel through space at 300,000 kilometers per second. How is 300,000 kilometers per second converted into meters per second? Well, we have kilometers, and kilo means 10 to the power of 3 or 1,000. They are the same thing. So we're going to have to do some timesing by 1,000, aren't we, to get from kilometers to meters. There are going to be more meters than there are kilometers, clearly. So where do we have times by 1,000? Not here. Oh, this looks good. Not here, not here. So the answer must be B. 300,000 times 1,000 is 300 million meters per second. Question F. They always ask this question, and we all know the answer, don't we? What is the equation which links frequency, wavelength, and speed? And full marks will be given if you just write the simple formula: V equals F lambda, or velocity is frequency times wavelength. Beautiful. Okay, now it's asking me to calculate the wavelength of the radio waves emitted from the distant galaxy. Give your answer in meters. Okay, so if V equals F lambda, let's have a look, let's write that out. So V equals F lambda, and it wants me to work out the wavelength. Let's work that out. The wavelength is going to equal, thank you, lambda is going to equal V over F. V, we all know, is 300, 1, 2, 3, 1, 2, 3. So it's 3 times 10 to the power of 8 meters per second is the speed of electromagnetic radiation. That's the velocity, and the frequency, which was given in the previous part of the question. Students often get confuzzled or confused by where does the number come from, and if you flick back to the previous page, the exam board are very good at putting a question over 2 pages and putting the number at the beginning of the question. And here we are at part G, and you're wondering where the number is. The number is at the beginning of the question. These cancel out, that all cancels, that all cancels. It's 3 over 12, isn't it, which is 1/4. So the answer is 0.25 meters. Congratulations if you got that one correct. Okay, figure 2, we can see immediately it's a longitudinal wave. We've got areas of compression and rarefaction on the wave. So here is my compression, here is my rarefaction, or where the wave is spread out. The question is, which of the letters on figure 1 shows a centre of rarefaction? Oh, I've already answered the question. It is clearly at K. Which 2 letters in figure 1 have a distance of 1 wavelength in between them? Well, don't forget, 1 wavelength is 1 full cycle, or 1 part of the full spectrum, which describes the whole spectrum. So it can be from peak to peak, or trough to trough, or 2 consecutive points on the actual wave. So here we are on our wave at the top. It's not going to be between J and K, because that's kind of just about 1/3 of a wavelength. 2 consecutive areas. So here's a compression, here's a compression, and the other 2 are far too small. So the answer must be between L and M on that slinky, I believe, which is at the top of this question. Part C, describe how the end of the stretched spring should be moved in order to produce a transverse wave. I'm sure your teacher has told you transverse waves have a perpendicular direction of travel in relation to the energy transfer. So describe how the end is moved perpendicular, or you could say at 90 degrees, so it's vertically up and down. Then the wave will propagate in the usual sine curve that you are, I'm sure, familiar with. Okay, all happy so far. Now we have 2 students. We have 1 student who is clapping a pair of cymbals and 1 student with a timer. So student A hit 2 cymbals together, and student B started a stopwatch. Great teamwork. When student A heard an echo, she hit the cymbals together again. So clap, boom, back, echo, boom, back, echo. Student B stopped the stopwatch after timing 5 echoes. Now they're already talking about 5 echoes, which suggests they're getting good data, reliable data, hopefully. Here are the students' results: 3.1, 2.7, 2.2, and 3.2. So the time, this is in seconds, so there's quite a range of data, isn't there? 2.7, 2.2 is the lowest, 3.2 is the highest. So there's a range of a whole second in there. But not asked me to do anything yet. What do you want me to do? Okay. The students decided that the time of 2.2 seconds was an anomalous result, so it didn't fit in with the rest of them. What was the most likely cause for the anomalous results? Well, let's have a look at that page again, 2.2. So look at 2.2, which is down here. It's results number 3. And let's do that in red just for a change. So this one is our anomalous result. Why is it anomalous? Well, it's 1 whole second adrift of the highest value. The next lowest, or the next range, if we remove the 2.2, would be 2.7 as the lowest and 3.2 as the highest. So that's only a range of 0.5. So we actually increase the validity of the data. So, which was the most likely cause of the anomalous result? Okay, what about not setting the stopwatch to 0? If you didn't set it to 0, you don't know if it was minus or plus 0, so I'm not sure about that one. Let's just think about that one for now. Starting it too soon, if you started it too soon before the cymbals were clapped, then that would mean that the time measured would be larger, so it's not that one. Timing less than 5 echoes, so it's significantly less. The time was significantly less than the other values in the table. So I quite like that one, but let's just look at the last one and see where we're going. And timing more than 5 echoes, clearly that's incorrect, because that would also give a larger value. Not setting to 0, I don't like that because it would be plus or minus. So the answer is timing less than 5 echoes. Don't forget, multiple choice are often the harder questions, and it's as much about eliminating the incorrect as it is about immediately going, yes, it's definitely that one. Okay. Calculate the mean value of the time for 5 echoes. Well, you'd have to take the... it actually tells you, happy days. Ignore the anomalous results. So there are only 3 pieces of data. So I've looked at the table, 3.1 plus 2.7 plus 3.2 equals 9.0. To get the mean, divide by the number of values that you've put into the equation. 9 over 3 is 3.0 seconds. Don't forget your decimal places should be consistent with the data that you've put into the calculation. Okay, part F. The distance between student A and the building is 75 meters. They're quite far away. Calculate the distance the sound travels in going from student A to the building and back again 5 times. Oh, it's 5 times. Okay, well, it's 5 times, but that's 5 times 2, isn't it? Because it had to go there and back. So that's 5 times 2, which is 10 actual journeys from symbol to wall back to the person measuring. And it was 75 meters. So it's 10 times 75, which is 750 meters. But we can read my writing on that one. Okay, 750 meters. Now there's bound to be a calculation. There always is. They're quite kind. They often give you or remind you of the equation in the question. So calculate the speed of sound. Use your answers to E and F and the equation. Speed is distance travelled over time. Well, that's fresh in our memories, isn't it? We've just worked out the distance travelled. So that's going to be 750 meters divided by the time, which was 3 seconds. So that's a straightforward 250 meters per second. As a good rule of thumb, it's really useful if you get a number which is a non-whole number, a non-integer number, then just worry and double check your calculation. It doesn't mean it's immediately wrong, but it tends to be for IGCSE to keep the numbers whole, I think is the best word, to keep the numbers whole. Okay. The value for the speed of sound obtained by the students is not very accurate. Suggest 2 changes to the method used by the students that would improve the accuracy. To improve the accuracy, I would do more than 5 echoes. Do 10, do 20, okay? You're going to get a much more accurate result. Why? Because you're averaging out all of the errors. Another way, you could have more than 2 students actually doing the measuring. Because clearly human beings are flawed individuals. We are not perfect, despite what some people think, and we do have errors. And when I see, or when I hear the cymbal sound coming back, and when someone else hears the cymbal sound coming back, will be different values, certainly by probably about half a second. And if you use 2 people and average across those, then you would improve the accuracy of the results, which is what the question is after. Remember, always double tap your answer. Look back at the original question. Does your answer the actual question asked? Okay, part 3. We're looking at a familiar ripple tank. Hopefully you've seen one of these in class, or you've seen a simulation of how to use a ripple tank. So the students adjusted the speed of the motor so that the bar hit the water more times each second. Times each second, we're already thinking of hertz, we're thinking of frequency. What happened to the frequency of the wave? Well, if it's more times per second, then I hope you all know the frequency of the wave indeed increased. Describe how the frequency of the water waves in the ripple tank can be measured. Well, frequency is measured in hertz. Frequency in hertz, Hz, which is number of waves per second, and it's only 1 mark. So if you just put number of waves or number of cycles per second, you would get that mark, and that would be absolutely fine on your way to a top result. Okay, the student measured the frequency of the water waves as 5 Hertz. Now it wants you to calculate the period of the water waves using the equation period is 1 divided by the frequency. So it's a simple matter of popping this into your equation. So it's 1 over 5, which is 0.2, and the period is measured in seconds. 4 small water waves are created in a ripple tank by a wooden bar, another ripple tank. The wooden bar vibrates up and down, hitting the surface of the water. The figure below shows a cross section of the ripple tank and the water. Which letter shows the amplitude of the water wave? Is it J? J here. Which figure shows the amplitude of the water wave? We've got K, got L. Right, so K is kind of in the middle there, isn't it? It's not quite touching the bottom there. L is the full. This is going from the bottom of the tank, so it's not that. It's not that. So the answer is J. Just be careful on your starting and end points for your amplitude. Okay. Question 9. Are you going to play? Yes, you are. The speed of the wooden bar is changed as the bar hits the water fewer times each second. Okay. You all know the answer to this one now, don't you? If it's fewer times per second, then the water wave is frequency is going to decrease. Thank you. Give my pen back. Thank you. Let's go back. It's going to decrease. Describe how the wavelength of the water waves in a ripple tank can be measured accurately. So, to get the wavelength, you need distance. So you can get a meter ruler. It doesn't have to be a meter. It could be 30 centimeter. Just get a ruler. You could time 10 waves, or the time it takes 10 waves to pass a certain point. Then divide those 10 waves by 10 to equal 1 wavelength. Don't forget, in science we're always looking for accuracy in our responses. You improve the accuracy by increasing the number of repeats. Question 10. The speed of a wave is calculated using the following equation. Speed is frequency times wavelength. Don't forget, speed and velocity are interchangeable. The water waves in a ripple tank have a wavelength of 1.2 centimeters and a frequency of 18.5 Hertz. How does the speed of these water waves compare to the typical speed of a person walking? Well, let's have a look. So, what we want to calculate are lambda is wavelength, which is 1.2 cm. That's here. Frequency is 18.5 Hertz, which is here. So V is velocity or speed is frequency times wavelength, which is here. So 1.2 times 18.5 is going to equal, hold on a minute, what have we not done? This is in centimeters. The wavelength is in centimeters, but the frequency is in hertz, which is in meters per second. So we need to, that's not 1.2 centimeters, that's 0.012 meters. Now we're happy. Glad we caught that, which is 0.22 meters per second. How is the speed of the water wave calculated, the typical speed of a person walking? I'm walking how many meters per second? Probably 2-3 meters per second, somewhere around there. So this is much slower than a person walking. Okay. Question 5. Some objects are transparent, light goes through, and some objects are opaque. It does not. So which one of those objects is transparent? This is an insult to our intelligence, isn't it? Okay, moving on. Question 11. Complete the sentence. An opaque object does not, easy, free money, transmit light. A student wears a white t-shirt and a red baseball cap to a party. Why does the t-shirt look white in white light? Because if it's white, it will reflect all wavelengths. Don't forget, different wavelengths are different colours. White light is composed of all colours. Richard of York did battle in vain. You know the deal. D. Explain how the colour of the baseball cap appears to change when the room lights at the party change from white to blue. Well, it's a red cap. It's a red cap. Yes, it's a red baseball cap. So red cap, white light equals red, because this white light contains all of the colours. But from white to blue, or blue light. Blue is not the primary colour. Blue has no red in it, so it will appear black. A student investigated how the type of surface affects the amount of infrared radiation the surface absorbs. Figure 2 shows the equipment that the students used. There we have a radiant heater in the middle, and we've got the sheet of silvery metal, usually with a metal sheet, and on the right we have a matte black surface. The wax melts and the drawing pins fall off the surfaces. I've not seen anybody do this for years. They used to do this in school science, but it tends to be less popular now. In the investigation, there are several variables. Draw one line from each variable to the correct description of that variable. Control variable is the one that we keep the same to make sure that we have a fair test. Dependent is the thing that we measure, and independent is the one that we change. So control distance, well, that's good, distance from the metal sheets. Dependent was the thing that we're going to measure, which is the time. So hopefully independent are the different surfaces. Those are the things that we chose to change, and we are the correct answer. Happy days. Next question, what is the main hazard in this investigation? The main hazard is the infrared heater, because infrared radiation can burn human skin or flesh, if you want to be a bit more descriptive. The drawing pin attached to the matte black metal sheet fell off first. What can be concluded from this result? Well, that means that the matte black surface is a better absorber of infrared radiation. That's what can be concluded. It doesn't tell you what colour of socks that the experimenter was wearing, but it does tell you that matte black is a better absorber of infrared radiation. Okay, ultrasound is used to scan unborn babies, but X-rays are not. No, you don't use X-rays to scan for unborn babies. Why am I smirking? Why am I laughing? Well, it would not be very helpful to the unborn baby if you scanned it with X-rays. The ultrasound, let's call that US, is not ionizing. Okay, it's not an ionizing radiation. That means that the other point is that X-rays are ionizing radiation. Okay, the ultrasound is not dangerous. It is just sound waves, not dangerous. But X-rays, they can cause cancer, which clearly use ultrasound if you're looking at your baby in the future. B. The behaviour of ultrasound waves when they meet a boundary between two different materials is used to produce an image. Describe how. Well, the ultrasound, I'll use US as my shorthand again. Ultrasound is reflected from hard surfaces. Hard surfaces. Okay. Or it can be partially reflected. And then the time taken for the reflection, this will build up the image. Happy days. Okay, typical sort of question. Figure 1 shows two pulses from a scan of an unborn baby. The emitted pulse is labelled A. The returning pulse picked up by the receiver is labelled B. The closest distance between the unborn baby and the mother's skin is 4 centimeters. Let's underline that. We're going to need that in this response. Use information from figure 1 to calculate the average speed of the pulse. Okay. So what have we got? We've got 30 here, and 80. So the distance between A and B is 50. No, it's not seconds, it's 10 to the minus 6 seconds. Always read the axis, because they will try and trick you or catch you out or test you, which is what it is. It's a test. 50 by 10 to the 6 seconds. So we've got a time, that's T. Don't forget your 4 centimeters. That's going to be our distance. Okay. So speed is distance over time. So what we're going to do, we've got 0.0. So this is in seconds. But what we want to work out. Well, the speed, right? The speed, and the speed we want to have in meters per second. So that's the unit of speed. So this is in centimeters. So I need to make that 0.04 meters. Okay. So now it's 0.04 meters, but that's the distance from the baby to the mother's skin. Distance. And it needs to come back again. That's the time it took. So it's times 2. There's a sneaky little trick. And now if I divide that by the 50 by 10 to the minus 6, speed is distance over time. So this is just distance over time. Careful on the distance. It's double, remember, because here's the mum. That's a mum. There's the baby. And the time it took, I had to go from here to there and back again. Okay, so you had to times it by 2. That's where the times 2 comes from. If we do that sum, so 0.08 over 50 by 10 to the minus 6, I make that 800 meters per second. Okay. Do a couple more because I'm enjoying myself. 16. Describe how X-rays are able to produce an image of bones. Well, the X-ray is stopped by the bone, so the bone does not allow penetration of the X-rays. X-rays stopped by bone, but they are transmitted by soft tissue. Transmitted by soft tissue, and therefore it creates an image. X-rays are able to produce detailed images because their wavelength is very short. Look at your electromagnetic spectrum, it is very short indeed. Let's leave it after this one. Which of the following types of electromagnetic wave has the highest frequency? You've all learnt your electromagnetic spectrum correct. Let's finish off with a beautiful colour, purple, and the answer is clearly gamma rays. Alright guys, you can see one at the bottom. It's rude to leave you without answering that question. What makes microwaves suitable for sending communications to a satellite in space? Because they can travel. They can travel. Slim purple? Yes, we are. They can travel through our atmosphere on beautiful planet Earth. Okay, thank you very much for watching. Hope you found that useful. That was a review of the wave stuff that we've been doing so far. If this is of use, then I'll make one on electromagnetic waves and some of the electricity stuff that we're doing as well. Okay, don't forget, smash that subscribe button. Thanks very much for watching. Have a great day. I'm out of here.